My name is Ashley Hartwell, and today I'm going to talk to you about my work on the design optimization of two-way filler slabs. To start broadly, there is huge growth in the construction sector. The UN Environment Global Status Report in 2017 reported that we will build a new New York every month for the next 40 years. When looking at this from a materials perspective, we see that concrete is the leading contributor of CO2 emissions in buildings, with 2 times as much concrete being produced as all other construction materials combined. When looking at the embodied energy of structures, which is the energy the energy consumed in bringing a substance to a usable form, we see that in concrete frame construction, over 60% of total embodied energy contributions are from the concrete structure itself, and majority of that is from structural horizontal slabs or floor and roof systems. In parallel to this challenge, in many developing contexts, agricultural byproducts and waste are a pressing issue leading to the landfilling or burning of the material. Previous research has identified the possibility of incorporating agricultural waste as building material alternatives, and I'm specifically interested in the role these materials could serve as low embodied energy insulation. Lastly, it has been shown that integrated solutions can pose greater energy savings during a building's lifetime overall. So what structural system allows us to address both embodied energy and operational energy concerns? In a filler slab, the filler material plays at least 2 roles. It acts as loss formwork to remove unnecessary structural material, which results in a waffle slab-like structure, and can provide some thermal benefit. This technology was popularized by British-born Indian architect Laurie Baker, who proposed a solution to reduce the amount of concrete used in roof systems and therefore the overall cost. The animation on the slide breaks down a traditional filler slab with terracotta pots as the filler down to its constitutive parts. I won't get into the details of each of these studies right now, but I show them here to say I'm certainly not the only person concerned with the design of filler slab systems. I will pull out some methods used in these studies relevant to my work. The first study by Fiala in 2006 featured both environmental performance evaluation and optimization. Later in 2019, Gavali and Ralagankar largely focused on thermal performance, and most recently in 2020, Acharya examined thermal performance of filler slabs using optimization methods. My work provides a computational design method that addresses each of these: environmental performance, thermal performance, and structural optimization. Here's an example of an optimized design result from the study I performed. We see that when compared to the minimum depth flat concrete slab, a 32% or 36% reduction in embodied energy, an 85% reduction in thermal transmittance, and a 32% reduction in structural mass. Now I'll show my methodology to obtain these results. First, we do a material study to choose traditional and alternative materials that would be good candidates for the design location. That goes into a parameterized model of the geometry. The structural model accounts for embodied energy and mass while ensuring the design is structurally safe and meets code. The thermal model calculates the U value of the component using a weighted average methodology. Manipulation of the computational model happens within a loop via a single objective optimization algorithm. This happens until the optimal performing design solution is produced and the algorithm terminates. Let's dig into the filler material analysis and selection. We start by examining traditional structural materials, traditional insulation materials, and emerging regionally available alternatives for both. The emerging materials are low cost and are made from locally available agricultural waste, such as bagasse and ash composite boards and straw bales. The materials mentioned in the previous slide are plotted here with respect to embodied energy and density. Concrete is pointed out with the black arrow. Materials in the white region perform worse than concrete with respect to those 2 metrics. Similarly, this plot shows thermal conductivity and density, and we see that every material performs better than concrete to varying degrees. We can look at these 2 charts together, and we can say that if a material falls in the white region of both of these plots, then a single objective optimization can be pursued as a solution that minimizes both the embodied energy and will also minimize thermal transmittance. Here, we also make use of a scaling surface, which is a geometric dimensionality reduction method that decouples the design variables and the number of elements to be sized through a surface. It is frequently used in my research group to size apertures and structures. Here, I use this method to size the voids in the filler slab and reduce the number of variables in the design space. As mentioned before, this is a single objective optimization because of our material selection studies, because of how we use our material selection studies to select our filler materials. I'll also note that two types of constraints were considered, structural ones and geometric ones, all dictated by Indian building code. This constraint setup was inspired by the work on shaping one-way systems developed by my colleague, Mohammed Ismail. Here are the results for 3 filler materials studied: straw, Bagassian ash composite, and rock wool, for 3 different spans considered in the study of 6 meters, 9 meters, and 12 meters. Thermal transmittance is reduced. Here we see that thermal transmittance, or the U value, is reduced across all samples because a significant part of the volume of the slab is replaced with a more insulating material. We also see that only straw showed reduction across all metrics of interest. To dig into that result more, let's look at our best performing solution. So here is the solution for a 6-meter span with a straw filler, here we see our 3 performance metrics on the far right and 2 properties of interest, especially as we consider our objective function of reducing embodied energy. We see a reduction in steel use, which is important to lowering the embodied energy, but what was most fascinating about comparing these selected solutions to the benchmark is the depth comparison. What this demonstrated is that building efficiently with respect to embodied energy meant that we aren't just carving material away, but requiring an increase in structural depth overall. In conclusion, we see that the design of filler slabs is a multifaceted research problem, but there is a way that we can use computational design methods to find optimal designs for a variety of objectives that are important to stakeholders at every stage of the life of a filler slab. Thank you.